December 15th, 1941. Bletchley Park, a sprawling country estate 30 miles north of London, sits beneath a gray winter sky. In one of the concrete huts scattered across the grounds, a young mathematician named Alan Turing sits before a machine that shouldn't work. It is called the bomb, and it represents humanity's answer to what many believed was an unsolvable riddle. Outside, the war rages with undiminished fury. German U-boats are sinking merchant vessels faster than Britain can replace them. The Wehrmacht's advances in North Africa seem unstoppable. Hitler's forces control most of continental Europe. Yet in this quiet corner of Buckinghamshire, something extraordinary is unfolding. A battle fought not with guns and tanks, but with mathematics and mechanical ingenuity. Every day, the bomb clicks and whirs through billions of possible combinations, searching for a secret that, if found, could reshape the entire course of the Second World War. The intelligence officers waiting outside the hut understand the stakes. They know that somewhere in the ether, German commanders are sending encrypted messages that will determine the fate of convoys, the success of military operations, the survival of thousands of soldiers. And they know that if the encryption can be broken, if these messages can be read as casually as a newspaper headline, the advantage might finally shift towards the Allies. This is the story of how one man's obsession with pattern and logic became one of the war's most closely guarded secrets, and how the solution to an apparently impossible problem altered the trajectory of history itself. The German military, particularly the Kriegsmarine and the Luftwaffe, had for years placed absolute faith in a machine called the Enigma. It was not a new invention. Its basic principles had been patented before the First World War, but the Germans had perfected it, militarized it, and distributed it throughout their armed forces with almost religious confidence in its impregnability. The Enigma machine resembled a typewriter crossed with the workings of a clock. When an operator pressed a letter on its keyboard, an electric current would travel through a series of rotating drums, or rotors, each one scrambling the signal in a different way. The letter that emerged on a panel of illuminated bulbs would bear no relation to the original. The genius of the system lay in the rotors movement. Each time a letter was encrypted, the rotors would advance by one position, changing the substitution pattern. This meant that the same letter pressed repeatedly would produce entirely different outputs. An A might become an X, then a K, then a Q. To decrypt a message, an operator needed to know the precise configuration of the rotors, their order, their starting position, and the plugboard settings that further scrambled the signal. With multiple rotors offering millions of possible combinations, the odds of cracking a single day's settings seemed astronomical. The Germans believed the figure was somewhere in the region of 150 million possible configurations. They were not entirely wrong. Yet they made a critical assumption that no single machine could test enough combinations quickly enough to matter. They reckoned without the ingenuity of Polish mathematicians, and later the British assault on the problem. The story of breaking Enigma did not begin at Bletchley Park. It began in Warsaw, where a brilliant Polish mathematician named Marian Rejewski had, in the 1930s, achieved what many thought impossible. Using pure mathematical reasoning and access to a commercial Enigma machine, Rejewski had reconstructed the internal wiring of the military version. He and his colleagues had even built their own machine, which they called the Bomba, named after a Polish ice cream dessert, though the name would later acquire a rather different resonance. When Germany invaded Poland in September 1939, the Polish intelligence service hastily shared their work with French and British counterparts. It was a gift of incalculable value, yet it would soon become obsolete. The Germans, operating on the principle of never trusting their own security assessments, periodically made subtle but catastrophic changes to their Enigma procedure. In May 1940, they introduced a fifth rotor to machines destined for the U-boats. The complexity multiplied exponentially. The Polish breakthrough was suddenly rendered useless. The situation facing British intelligence was dire. The Battle of the Atlantic was reaching its crisis point. German submarines were coordinating their attacks with a precision that suggested they could either predict convoy movements or, more terrifyingly, read the wireless traffic of the Royal Navy. Every day that the Enigma remained unbroken meant another 3, 4, sometimes 5 merchant ships sent to the bottom of the ocean. The loss of cargo was devastating. Fuel, food, munitions, all scarce commodities needed for survival. But the loss of life was, to those charged with the war effort, even more strategic a consideration. Morale among sailors was fragile. The crews manning these vessels knew that every voyage might be their last. In September 1940, German submarines sank 50 ships in a single week. The figures grew worse through the winter. The naval historians would later calculate that Germany came closer to strangling Britain into submission through submarine warfare than through any other means. And the key to that stranglehold was not superior tactics or ship design, but rather the security of the Enigma machine. Someone had to break it. The task fell to an unusual collection of mathematicians, linguists, classical scholars, and codebreakers assembled at Bletchley Park. The bomb machine that Turing and his colleagues, including Gordon Welchley, who had worked on the mathematical problem, and engineers who understood the mechanics, designed was a direct descendant of Rejewski's Bomba, but it was far more ambitious. Where the Polish machine had exploited specific weaknesses in Enigma procedure, the British machine would attempt something more radical. It would systematically test rotor configurations at mechanical speed. The machine itself was formidable in scale. Imagine a cupboard roughly 3 meters tall, 2 meters wide, and nearly 1 meter deep, about the height and width of a standard kitchen refrigerator, but considerably deeper. Its exterior was painted in functional gray, interrupted by rows of switches, plug boards, and indicator lights. Inside, the complexity was staggering. The bomb contained multiple sets of Enigma rotors, all turning in synchronization. At the machine's heart were hundreds of electromagnetic switches, each one capable of testing a different hypothesis about the rotor configuration. When the machine was switched on, the rotors would spin at extraordinary speed, far faster than a human operator could manage. Some early versions could test approximately 17,576 different rotor positions per second. To understand the magnitude of this achievement, consider that a human operator, working with pencil and paper, might test a single configuration in 5 minutes. The same test took the bomb roughly 0.06 seconds. The machine's rotors were driven by an electric motor, and as they spun, they produced a peculiar sound. Not quite a hum, not quite a whine, but something between a grinding and a chattering. Operators grew so accustomed to the noise that those who worked at Bletchley Park would later describe the sound as strangely comforting. Silence meant a breakdown. The process of using the bomb required a delicate balance between mechanical power and human intelligence. The cryptographers would first examine a day's intercepted Enigma traffic. They would look for patterns, repetitions, formulaic phrases, known structures. A message beginning with a weather report, for instance, might offer a point of entry. If the operators could deduce what plain text corresponded to what ciphertext, they had what was called a crib. They would feed this into the bomb, along with an assumption about the rotor order. The machine would then test every possible starting position for those rotors until, theoretically, it found the one configuration that would satisfy the crib. When it did, a bank of lights would illuminate and the bell would ring. Operators would rush to photograph the settings, reverse engineer the exact configuration of the plug board, and within hours, teams of young women, many of them fresh from school, would begin decrypting the day's messages by hand using the recovered settings. The entire process, from intercepted message to decrypted intelligence, might take anywhere from a few hours to a few days, depending on variables beyond the operator's control. But here is where human brilliance intersected with mechanical power. The bomb could never have worked without the cryptanalytic insight of the people operating it. The machine did not understand language or strategy. It simply tested combinations. It was the people of Bletchley Park who understood which combinations to test, who formulated the cribs, who recognized patterns in the noise of intercepted signals. The manufacturing of the bombs was itself a remarkable feat of industrial organization. The first machine was completed in March 1940 and installed at the Government Code and Cipher Schools facility, but one machine was clearly insufficient. By 1941, the British cryptanalytic effort required dozens of bombs, each one representing hundreds of hours of engineering labor. The machines were manufactured by the British Tabulating Machine Company, a firm located in Letchworth, Hertfordshire, about 30 kilometers from Bletchley Park. The company had previously specialized in punch card machines for accounting and census work. Now they were repurposed into one of the most critical manufacturing operations in the British war effort. Each bomba was essentially built to order, its internal configurations adjusted based on specific requirements derived from the particular variant of Enigma being targeted. The complexity of constructing these machines meant that no two bombs were identical. Skilled engineers worked from schematic drawings, hand-assembling rotors, carefully calibrating switches, testing and retesting each component. By the end of the war, over 200 bombs had been constructed, some at Bletchley Park itself, others at the Tabulating Machine Company, and several at an American facility in Washington, D.C. by a team of American engineers who had been initiated into the secret. The exact numbers remain somewhat shrouded in classification, but historical records suggest that at the peak of operations in 1943 and 1944, somewhere between 50 and 100 bombs were running simultaneously across the British cryptanalytic establishment. Each one consumed significant electrical power, enough to notice in the daily accounts of Bletchley Park's electricity consumption. The security around these machines was extraordinary. Only a handful of people knew the full scope of the operation. The engineers who built them knew only that they were manufacturing secret war machines. The operators knew only that they were processing messages. Only the very top echelon of the intelligence hierarchy understood the true scale and significance of what was being achieved. The bomb did not work instantaneously, and it was far from infallible. It offered probability and possibility, not certainty. Yet when it worked, and increasingly through 1941, 1942, and beyond, it did work. The intelligence it provided was of staggering value. Consider the case of Bismarck, the German battleship. In May 1941, the vessel had escaped into the Atlantic, posing a direct threat to British naval supremacy. The Admiralty was desperate to locate it, to engage it before it could wreak havoc on the merchant fleet. Naval intelligence, working with decrypted Enigma messages, was able to track the ship's movements with remarkable precision. They knew which harbors it was approaching, which supply ships were being sent to meet it. The intelligence did not come from a single decryption but from a sustained effort, Enigma message after decrypted Enigma message, each one confirming or adjusting the naval officer's understanding of the battleship's position and trajectory. Within weeks of its breakout, Bismarck had been located, engaged, and sunk. The official history credited the intelligence to various sources, but those in the know understood that Enigma decryption had been crucial. The security of this knowledge was so paramount that for decades after the war, the existence of the bomb remained classified. If you are finding this interesting, a quick subscribe helps more than you know. It means more people discover these stories of how intelligence, mathematics, and engineering shaped the outcome of the greatest conflict in modern history. The German military, by contrast, possessed no equivalent to the bomb. They had their own cryptanalytic efforts, their own attempts to break Allied ciphers. The Germans had broken the Italian cipher, for instance, and had significant success against French and American codes. Yet they seemed almost complacent about Enigma's security. Interrogated after the war, German intelligence officers expressed genuine shock when they learned that their supposedly unbreakable cipher had been read throughout the conflict. The Germans, following their principles of rigorous engineering and systematic security assessment, believed that the mathematical complexity of Enigma rendered it immune to attack. They had even conducted vulnerability assessments, theoretical exercises in which they asked whether a machine-based attack was possible. They concluded it was not. This miscalculation had strategic consequences that reverberated across the entire war. Nor were the Americans, despite their considerable resources, able to independently break Enigma in the early years. American cryptanalysts made significant contributions to the understanding of Japanese codes, particularly in the Pacific theater, but they lacked the head start that the Polish and British possessed. When American cryptanalysts were eventually brought into the secret, they participated in the effort, but the intellectual foundation had already been laid by the British. The comparison is instructive. Two nations with comparable technological and intellectual capabilities, yet one possessed the key that unlocked the enemy's secrets, whilst the other did not. The difference was not in raw ability, but in historical accident and initial courage, the willingness of the Polish intelligence service to share what they had learned, and the British willingness to build upon that foundation in defiance of seemingly impossible odds. The impact of Enigma decryption on the actual course of the Second World War remains one of history's most contested questions, and debates among historians remain vigorous. Some claim that Ultra, the designation given to intelligence derived from Enigma decryption, shortened the war by as much as 2 or 3 years. Others argue that whilst the intelligence was valuable, it was not decisive in any single campaign. The truth likely lies somewhere between these extremes, in the accumulated small advantages that, over months and years, shift the balance of a conflict. Consider the Battle of the Atlantic in isolation. By late 1942, the German submarine menace seemed ascendant. Losses were mounting. The American entry into the war had brought fresh shipping resources, but the submarines were sinking vessels faster than replacements could be built. Then, from 1943 onwards, the losses stabilized, then declined. Naval historians attribute this not to any single factor, but to a constellation of improvements: better escort vessels, improved detection technology such as radar, and, crucially, the ability to locate and anticipate submarine movements. That last element derived substantially from Enigma intelligence. The decoded messages told Allied commanders where the U-boats were gathering, what their fuel reserves were, which ships were being sent to resupply them. With this knowledge, convoys could be routed to avoid areas of concentration. Submarine wolf packs could be intercepted before they could attack. The psychological impact of this shift was almost as significant as the material one. German submarine commanders who had enjoyed months of relative impunity suddenly found themselves on the defensive. Losses mounted. The morale of German naval personnel, once supremely confident, began to crack. Grand Admiral Dönitz, commander of the submarine service, eventually withdrew from the Atlantic convoy routes, acknowledging that the advantage had shifted beyond recovery. Whether this outcome would have been reached without Enigma decryption is unknowable, but it is certain that the intelligence accelerated the process. The invasion of Normandy offers another example. The Allies knew from Enigma decryption that the Germans had been deceived about where the invasion would occur. The elaborate deception operation, codenamed Fortitude, had convinced German high command that the primary thrust would come at Pas-de-Calais, not Normandy. After the beaches were secured, as German reinforcements were being deployed, Enigma messages confirmed that the Germans still believed this was a secondary landing. The intelligence allowed the Allies to take calculated risks, confident that German responses would be delayed and misaligned with actual circumstances. Again, decryption did not make the invasion inevitable. The scale of the Allied effort, the quality of training, the courage of the soldiers themselves, these were the true decisive factors. Yet the intelligence provided a measurable advantage at a moment when advantage was precious. In the Mediterranean, in North Africa, in the Pacific, though here the intelligence was primarily Japanese rather than German, decrypted enemy communications provided the Allied command structure with a clarity of understanding about enemy intentions that no amount of conventional intelligence gathering could provide. Messages intercepted and decrypted today could inform operations tomorrow. This speed of intelligence was transformative in a conflict where the initiative could shift in hours.